So we're dealing with this orthogonal projection. Well, the distance from any point to a linear space F, which is just simply defined as the infimum, or the minimum, the smallest norm that you can get when you're doing that point x minus some point u that belongs to this linear space, and actually it's going, this minimum value, this infimum, is going to be attained for u is equal to the orthogonal projection of x on f. Okay, why is that? That's very simply, that's just consequence of the Pythagoras theorem. Okay, you've got your point x here, right? That vector x. Well, again, you can visualize it in 2 and 3 dimensions, and it's easier to conceptualize, but then that can be applied to any kind of linear space, as long, well, any kind of pre-Hilbertian spaces. It means as long as you have a well-defined inner product and a way to define these distances, and, well, the norm and the orthogonality. So you've got your point x, and you want to consider any point u that belongs to the to the space F. So that could be here, that could be here, that could be here, and you're computing the distance between u and between x and u, so that's x minus u. X minus u could be here, could be here, okay? And you want to keep the u such that you get the smallest distance, all right? And very naturally, this is going to be achieved by the orthogonal projection, okay? So let me just clear a bit this drawing. So you've got your point x. If you have any u here, okay, so that's x minus u, and what can you write? You can write that x minus u can be expressed as, so that is always true anyway, that's just chance relation, that's x minus p of x plus p of x minus u, okay? And p is, let's say that p of x, pf of x is the orthogonal projection of x on f. So what do we have? We have, well, orthogonality. That's what it's for, right? So we have orthogonality between x minus p of x, okay, x minus p of x. That's going to be orthogonal to, well, p of x, to anything to that belongs to f, okay? That's going to be orthogonal to u, okay? So this is going to be orthogonal to anything that belongs to f, and in particular, that's going to be orthogonal to p of x minus u, because p of x, it's that one, all right? It's the projection on f, so it belongs to f, and u is that one, it belongs to f also, okay? All right, well, u is whatever vector, depending on where the 0 is, anyway. Okay, so the important thing is that you have this orthogonality between those vectors, and so that now if you write the distance, oh, maybe I can keep this drawing, it's a nice one. If you write the distance square, x minus u square, okay, applying Pythagoras theorem, you know that, so that distance here, okay, you know that it's going to be the sum of, well, sorry, let me rewrite this as x minus p of x plus p of x minus u, okay, square. And applying Pythagoras theorem, I know that as these ones or two orthogonal vectors, this is just going to be the sum of the squares of those norms. That's x minus p of x square plus p of x minus u square. Okay, you can visualize this right angle triangle on the above drawing, but it's so we know that it's still stands in any linear space. Okay, and so we want to minimize this amount, this value. Okay, we're looking for this minimum. All right, and of course it's going to be smallest when you can cancel out one of the terms. Right, so this is going to be um, as this is true for any u that belongs to f. In particular, it's going to be true for u is equal to p of x, and the good thing is that it cancels this out these terms, and finally we get that this minimum is equal to this value. Right, and so that the orthogonal projection gives you the smallest distance between a point and a linear space, which is, well, again, it's all very intuitive. That's why we did that for. Okay, so let's apply this to some simple example. All right, so let's see the following stuff. Simple example in R3. So if the question is, we have a plane. Let's take a plane when I can write. Plane of equation x plus y plus z equals to 0. So that's all in R3. Let's take a point or a vector. Okay. So now you understand that we can consider them the two ways. There are points and vectors at the same time, right? X is equal to 1, 2, 3. Okay, and I want the distance between the point X and the plane, right? So probably you remember, as you probably have seen that in many ways. So one way to do that is to say that your point X as projection, let's call that P of X, and this vector then X minus P of X is collinear to the normal vector to the plane. All right, the normal vector you remember from what we did a bit earlier, or maybe from before that. The normal vector here is going to be given by, well, in our case, the vector 1, 1, 1, because the equation of the plane, it comes directly from the fact that it's going to be all the xyz such that they are orthogonal to the normal vector. Okay, I should have written both in columns, but if you write that xyz, it's the points of R3 with coordinates xyz that are orthogonal to vector 1, 1, 1. You're really writing that the dot product of xyz with 1, 1, 1 is equal to 0, which gives you the Cartesian equation of the plane. So x plus y plus z is equal to 0 in our case here. Okay, so that was one small thing to say. So x minus, so let's go back to our projection. So one thing we have, if we want to, so we want to find the distance between a point and the plane. So the idea is to find the orthogonal projection and calculate the norm of x minus p of x, where p of x is the orthogonal projection. So basically we need to find p of x. So one way to do that, maybe you even did that in year one, was to say, well, I'm looking for p of x, and how can we define it? We know that x minus p of x is going to be collinear to n to the normal vector, and another that is going to be give you one thing, which just tells you that if p of x has coordinates um, has coordinates small x, y, z that you're looking for. X minus p of x, big X, sorry, minus p of x is going to be given by x minus 1, y minus 2, z minus 3, and we know that it's going to be collinear to n, so it's equal to some real number times this normal vector. Okay, that gives you one first equation for the x, y, z. X minus 1 is equal to k times 1, and y minus 2 is equal to k times 1, z minus 3 is equal to k times 1. And you get a second set of equation by saying that p of x actually belongs to your plane. Okay, so what does that mean? It means that the x small x plus y plus z is equal to 0. So now you can substitute smaller x by what you get from the first set of equation. Okay, so x minus 1 is equal to k, y minus 2 is equal to k, and z minus 3 is equal to k. Sorry, that's a z, that's a 2. So basically that x is equal to k plus 1, y is equal to k plus 2, z is equal to k plus 3. And so you substitute those values in the equation, in the Cartesian equation of the plane, and that gives you, you get 3k's is equal to 3k's is equal to -6, so k is equal to -2, so that x minus p of x is equal to x minus, sorry, big X big X minus p of x is equal to the vector -2, -2, -2. That's it. So that if you're doing, then if you're doing the distance between x and f, that's the norm of x minus p of x, big X minus p of x, and that's going to be given by square root of 2 square plus -2 square plus -2 square. That's square root of 12 to square root of 3. What's the other way to do that? Well, let's do some projections the way we've just learned how to do that. The nice thing, well, what is going to be easy, so you know that when you're doing a projection, P on F, you need a linear, an orthonormal basis of F. So in our case, we would need two vectors, and the projection on F of any x is going to be given by scalar product x e1 times e1 plus scalar product x e2 times e2. Okay, the thing is that now we've got, we could find an orthonormal basis of this one, but actually there's a much simpler way to do it. We're going to use the orthogonal direction. So if that is f orthogonal, okay, f orthogonal. Why is that? Because it's much simpler to get an orthonormal basis of the orthogonal direction. Why? Because we only have one single vector. We don't have to worry too much. We don't have to build the orthogonality. Actually, I will need to open a new video for this because my time for this video is done.